All right, they're recording. Okay, now today we want to talk about cryptographic foundation. In this note, we are going to discuss some fundamental cryptographic concepts and especially hash functions, public and private keys, and digital signatures, and Bitcoin's UTXO, and they form the backbone of a Bitcoin security and functionality. And then I will also talk about operational code, OP codes, and then these are the set of instructions Bitcoin uses. Okay, so all right. First off, hash function. Hash function SHA-256 is a one-way cryptographic algorithm that takes any input data and produces a fixed size string of characters. We call it hash or digest that appears random. So this looks random, and it's actually a random integer. Okay, if you use a hexadecimal, and Bitcoin uses the SHA-256 hash function extensively, and it is called a 256-bit hash, or, typically it is represented as 64 characters hexadecimal number. Okay, hexadecimal, you know what it is, right? 0, 1, 2, all the way up to A, B, C, D, E, F, right? So, yeah, so properties of cryptographic hashes. It is a one-way function. Basically, given an input, it is easy to compute the hash, but nearly impossible to reconstruct the original input from hash. It is a deterministic function. So this hash function, given input number 1, then this will produce output 1 all the time. Same input, same output. That's what we mean by deterministic. It's not a random function. But this output, which is a 256-bit hash, that looks random. That's what it is. So if you change a little bit in the input, the output changes dramatically, and that number looks random. So that's what it is. And it is called avalanche effect. A tiny change in input, even changing a single letter from the uppercase to lowercase, or you place a start in the sequence, in the sentence, it will dramatically change the hash output. For example, the hash of hello world will be completely different from small letter hello world. Okay, so this a small change produces entirely different hash output. That's what it is about avalanche effect. And it has collision resistant feature in it. So it is infeasible to find two different inputs that produce the same hash. So basically, But what this means is this. So you have F, oh, hold on. Mhm. All right. Little bit of happening. All right. So you have two input. Let's say input one produced hash, and another input F input two, which is different from this hash in one. Okay. So in one, in two are not the same, but they produce the same hash. Same hash. This is possible. Theoretically, this is possible, but in practice, this doesn't happen. Okay, that's what it means. It is infeasible to find two different inputs that produce the same hash. This is crucial for security and ensuring that each piece of data corresponds to unique hash fingerprint. Okay. This is possible, but you will never encounter such events in your lifetime. So that's what it is. And immutability via hashing. In the Bitcoin blockchain, hashes ensure data integrity because of this one-wayness, because of these properties of a cryptographic hash function. Okay, and that is the resource for immutability. And miners use SHA-256 in Bitcoin's proof of work. We will talk about that. All right. And you can read about this other stuff. All right. So here is the hash function in a little bit greater detail. So I have a message, Bob, I love you, comma, Alice, comma, and the hash function. So this f is a function that I'm using in this node. So h here is a hash function. Put this message as an input, then you get this 64 hexadecimal output. So this is a number. This is an integer. Okay. The string of 64 hexadecimals, or because each one is 4-bit integer. So basically, 4-bit string. So basically, you have 256 bits. Okay. So this is hash output. Okay. This is the input. Okay. All right. But here, uh, let's take a look at it. So X1 is the message, as you can see, and HX1 is hash output. It starts with the 2FE and ends with the 34. Okay, and the X2, Bob, I love you, Alice, no comma, right? Then you get a completely different hash output. B13 and ends with 25. So this string and this string down here are completely different. That is what we call avalanche effect of hash function output. Okay, so another example, Bob, I loved you. So there is a D included, and then you get a completely different hash. Okay, so another example of avalanche effect. So if you change a little bit, in the input, you get a completely different output. And then you use this property in Bitcoin's POW, proof of work. Okay, time difference, fixed difference. All right, and here secure hash function again, age, SHA-256 hash function age. So X is the set of inputs, possible input. As you can see, it could be message or files. The space of X is much more greater than the space of output Y. Okay, Y is just the space of 256 bit, 256 binary bits. Okay, or 64 hexadecimals. So this is a space of numbers. Basically, this is a space of numbers 0, 1, 2, all the way up to the power of 256 minus 1. So this is a number space, only a finite number of elements. Okay, the total element is 200 to 2 to the power of 256. There are only this many elements. How many elements here? Much more than 256 bit element. Okay, so all right, so that's what happens. But I love you at least with no point to get output, which is completely different from the first one. And then there is a SHA-256 algorithm. You can take a look at this NIST, National Institute of Standard and Technology document right here, and then you can take a look at more. And here, as you can see from this file right here, here is the input and returns concatenated output, which is 256 bits, right? And calculation of this output involves modulo operations, a lot of addition operations, and going through some internal functions, and yeah, lots of things are happening here. A lot of additions, multiplications, and modulo operations. The output looks gibberish, right? And that's it. And here is the now functional input-output relation. Okay, so suppose that X, the input set, is a message up to 2 megabytes inside. I have 1 megabyte inside. Okay, so basically a block is a 1 megabyte, and then we can imagine that there are garden variety of different axes, inputs, right? Yeah, different inputs. And here is one file. One dot is the one file. Okay, hold on. One dot is a one file. Okay, hold on. Okay. One dot is a one file. So you take one file out of this many, put it as an input to the hash function. You select one X, so this one X, and then you produce output small y. Small y is 64 hexadecimal number. Yeah, this is your small y corresponding to this one. As you can see, this set is very, very large. But this one is only 200, 60 feet, 6-bit string. So it is a small, much more smaller set. This y is much more smaller than X. All right, that's one thing that you need to notice. And so let's take a look at the cardinality of the output hash set. Okay, so it is 200 power of 56. So in decimal, it is 10 to the power of 77. Okay, 77 decimal number. Okay, all right. So that's the size of the output. Okay, and what is the meaning of collision free? Okay, the size of the hash output set is so huge, 10 to the 77. So how big is the 10 to the 77? So one knows there are a large number of collisions, but that is possible, but one cannot come across any collision. That's what it is. Okay. So how? Because that is because 10 to the 77 is so big. Okay. So number of cells in a human body is 10 to the power of 13. Number of cells in all human body is 10 to the power of 23. Number of stars in the observable universe, 10 to the power of 22. Number of atoms in observable universe is 10 to the power of 80. So this one is kind of closer to number of atoms in all universe. Okay, so you never encounter one of these event. Okay, collision event. All right. So that's the meaning. Right. Now here is the POW puzzle. Okay. Hey, so now I'm using F for H, previous page H. Right. So same notation F, X. Okay. Same notation. And then Y is the hash output. Right. And then hash output Y is 256-bit integer. Okay. 256-bit integer, 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 and then integer, you can uh, compare with the target integer, or target number. Okay, so f x is a block header of Bitcoin blocks, as you as we have covered. We have a block header and block body. Block body is made of Merkle hashes, and then here there is a Merkle hash. Okay, and then version number, difficulty, all those are recorded in block header. Okay, you put this block header as an input. There is a nonce as well, counter. And if you include this block header, the output is a hash. That hash is 256-bit integer. You compare that with the target. All right, so here is the range of output. The largest one is this one, smallest is 0, right? And then let's suppose there is a target. Right, so this is output smaller than the target. So we are talking about this set. Okay. All right. So the size of the set that this can be satisfied is this large. Okay. 0 to target. Okay. And if it is greater than that, then this equation is not satisfied. So this is satisfied, not satisfied. Okay. Right? If it is not satisfied, then you change the nonce in the block header, which is a counter. Then you put it into the hash function again, because of avalanche effect, you get completely different output. Okay, and then you find out if this inequality is satisfied or not. Okay, if it is satisfied, then you hit the uh, right block header. Okay, then this equation satisfied, then you found the proof that uh, proof of your work. Okay, so for a block, find the nonce that satisfies the above inequality. So that's a work. Record the nonce or the block header. Record the nonce in the block header, and that's your proof. Okay. All right. So that's that. Then uh, by changing the target, I can control the difficulty level of Bitcoin POW puzzle. Okay. So here is a simple example. In this set, which is 256-bit string, there are white balls and black balls. Okay, white balls are 64 hexadecimals with 4 leading zeros. 4 leading zeros. So this is a number smaller than you know, a target, right? The target is smaller than, so target here 4 leading zero um, is we can set it to be 240. Okay, 4 leading zeros hexadecimal. We can set it to be this, right? And any hash smaller than this target is going to be white balls. Okay, so white balls are, so this is the set of axes, right, such that x is smaller than target, right? Size of that set is, the cardinality of this set is 2 to the power of 240. Okay. Now you can calculate the probability P that a single hash satisfies the POW. Okay, that is 240 divided by 200 to 56. So that is going to be 2 to the minus 16. So that's the probability of hitting, satisfying the inequality, satisfying this inequality. Oh, I forgot the hash. F hash is smaller than P. Yeah, F hash is smaller than. Or in terms of Y, uh, basically Y smaller than pi. Anyway, so that's the probability of single hash output hitting, satisfying the inequality. And then basically you can control the difficulty by uh, varying the target, right? Uh, so any hash looks like this, but a good hash value looks like this, a number smaller than 200 to 40. Okay. All right. Now let's move on. Same thing. And here, Arlene Tupo, uh, uh, proof of work is alone impossible, together possible problem. So let there be a CPU which can take one input and give one output. What is the probability that this CPU finds a good summary, good hash in a single hash cycle? That's this probability. Okay. Difficulty of POW puzzle can be adjusted by varying the size of the set A or varying the threshold, which is target. Okay. If you vary the target, you can change P, the probability. Okay, so P actually can represent a difficulty of a puzzle. Okay, change the P by varying the size of set A, which can be obtained by varying the target. All right. Given the difficulty P, or given the probability P, we aim to find the probability of mining success. Mining success. Okay. Mining success. All right. Definition. Success random variable K. Let K denotes 1, 2, 3, the index of hash at which POW success occurs. For example, if K is equal to 4, means that POW success comes exactly at the fourth hash. Okay, so you had tried first hash, it didn't satisfy. Second hash, it didn't satisfy. Third hash, it didn't satisfy. Fourth hash finally is satisfied. Okay, so what is that? Such a probability. So probability A equals 4 means, right? First trial, it didn't happen. And operation is and, right? First trial failed. Second trial failed. So it is end operation, right? And third trial failed. Fourth trial success. So these are all end operations. The first trial failed, and second trial failed, and third trial failed, and fourth trial success. So that's what this means. Okay. So this one is 1 minus p to the power of third p. Right. So if you let k equal to small k, the probability is 1 minus p to the power of k minus 1 times p. So that's the probability. Okay. All right. So this is a random variable since the draw of a successful hash is a random experiment. Okay. And here, hash rate of CPU. The hash rate of a CPU is defined as a number of hashes in a unit time. Okay, hash rate. Hash per second. Hash rate. Okay, that's what we are looking for. For example, the hash rate of a CPU, which can do 100 hash cycles in 1 second, is 100 hashes per second. Okay, and there are mining machines which are extremely fast. So this is the lecture note written 5 or 6 years ago. So currently we have an even faster machine, much more faster than these. But back 5 years back, we had these machines which are the fastest, right? So this one, for example, 14 tera hashes per sec, okay? So tera here is 10 to the power of 12 tera, okay? 14 tera hashes per second, so, okay, so a lot is really fast, right? That's a big number. Okay? And then success random variable, if we have a probability k smaller than or equal to k, if we do that, then this becomes a geometric distribution, right? Success first time, success second time, success third. So this is OR operation, right? Because this includes k equals 1 event, which is this one. K is equal to 2 event, which is this one, and so on and so on. And this one is OR operation, right? Because it is a union of such a set, right? All right, so that event that event, and then we have to take the union, k equals 3, and so on, right? So that's what is going on. And so it becomes a geometric distribution. It is a geometric. And the one that we have shown above, this one, this one, can be verified one more time with the geometric distribution, right? We use this notation to talk about this event, that is difference of the two geometric distributions, one at k, the other one at k minus 1, then it becomes this, okay? The one we have already proved, right? And this PMK, PMF, probability mass function. So we calculate the expected value, then it is nothing but 1 over P. Okay. So that's what it is. So yeah, that's 10 to the 6 hashes per block. Okay. So now you can change the Bitcoin difficulty in terms of leading zeros in the hash output. But if you do that, then basically there is a stepwise difficulty level increase, which is twice more difficult than the other. So that is the finest difficulty level. But you don't want that. So you want a finer scale. So we want to do finer scale adjustment of Bitcoin difficulty, and then we follow this. Okay, and officially the initial target is set to this number, 2 to the power of 224. So it has 32 binary leading zeros, or 8 hexa leading zero. So that is the initial difficulty. Initial target difficulty. Okay? Initial difficulty. Okay. Satoshi Nakamoto has used this one. Right? Ever since it is getting more difficult. Okay. All right. So currently, 5 years back, this is the number of hexadecimal zeros in front of the successful hash. Okay. And then in terms of target, the size is this one now. Okay. All right. So that's what it is. You can take a look at it. And when we take a look at the difficulty written in the block header, there are some number like that. And then if you take the log of that difficulty, that is kind of a number of leading zeros. And if you add 32 to this number, 41.68, 41.7 plus 32, this becomes number of leading zeros. So it is 73.7 leading zeros. All right. Okay, so that's in order to calculate P, the probability of hash success in a single run becomes this. The size of the set is this, right? So that is equal to 256 minus 73.7, which becomes this. Okay, 2 to the power of 182.325. That is the size of set A, and that divided by the total set size, then this becomes that, and then this becomes the P. So this is P. All right, you can take a look at it, and now we read the goal. Our goal was determining the hash rate, right? So we calculate the we know now, expected value of k, extract value of k is equal to 1 over p. So in order to solve this difficulty, we need to run this many hashes. We need to run this many hashes. Now, in order to find an answer in one block generation time, which is 10 minutes in the Bitcoin case, 10 minutes. In 10 minutes, you have to run this many hashes on the average in order to find the good hash. Okay? In 10 minutes, you have to run this many hashes. This many hashes. Okay? All right, so you divide 2 to the power of 73.7 divided by 10 minutes, which is 600 seconds. Then you get the hash rate. All right. So that's what we have done right here. So that is this number. So 5 years ago, the hash rate was 25 exa hashes per second. Exa is 10 to the 18. 25 exa hashes per second. That was the hash rate. So there is the, actually there was more than 5 years back, 6 or 7 years back. Okay. So back then there was tens of exahashes per second. Okay? 25 exahashes, 53 exahashes, 45 exahashes. That was hash rate back then, in 7 years ago. Now, September 2025, which we had the all-time Bitcoin price, all-time high of a Bitcoin price. The hash rate was at the peak, right? That was actually 1.1 Zeta. Zeta is 10 to the 21. Is Zeta. So that was 1.1 Zeta hashes per second. Okay, back then. Okay. All right, and now we are going to talk about digital signature and public key cryptography. So we can read about the public key cryptography. We have a private key and we have public key. Here I'm using K as a key, right? Small k is a private key. Capital K is a public key. Okay. So using the private key, you sign transaction. And then using the public key, you let others know, right? All right. And Bitcoin uses elliptic curve digital signature algorithm, okay? ECDSA, okay? And this one allows a user to sign a message or a transaction with their private key, all right? Anyone with the corresponding public key can verify that signature, but cannot forge a valid signature without the private key. So anyone with the public key can verify if the signature is valid or not. Okay, but it cannot. The person cannot do anything more than that. Only verification. Okay. All right. And then Bitcoin uses this to sign a transaction. Okay. If A want to send B, let's say one Bitcoin, right, one BTC, then there should be sign of A attached to it. Okay. So if this is registered into the Bitcoin network, then anyone can see this transaction. And then here B is actually uh, uh, person B's public key, okay, public, or an address driven from person B's public key, okay. So this is in general, for now, you can think of it as uh, public key of person B. Okay, so person B has the private key that leads to this public key. Okay, all right. So if this is given uh, in the blockchain ledger, then after this time point one, let's say time point one, after time after this time point, B can send C, let's say zero point 0.5 Bitcoin by signing this transaction. Okay, so that's the signature. Okay, then this uh, transaction can be utilized so that B can send another person uh, some of the money he got through this transaction. Okay, so that's what it is. Okay. All right. And then, okay. Bitcoin node in the network will check two things. The signature is valid for the given public key and that the public key has authorization. Okay. So this is done through cryptography, right? Mm. Right. So that's what it is. And security uh, is practically impossible to forge a signature without the key. All right. No one can uh, sign a transaction, right, with a valid outcome. Okay, with a valid outcome, right? Only the person who has the right private key can sign it, and then because other nodes in the network will verify if the sign is real or not. Okay, if there is any fault in it, um, the sign will turn out invalid. Okay, the only way the sign turn out valid is that the person pays it uh, has used the right private key. So that's what it is. But this part become controversial these days because there is a quantum computers with more than qubits, 1,000 qubits. This will happen maybe 3 or 5 years from now. Quantum computers with 1,000 qubits. Maybe Google makes it or some other companies make it, and there is a problem because there is a Shor algorithm. Shor algorithm, if we use Shor algorithm, from the public key, one can find private key. That's the threat, quantum threat, quantum computer threat. So can break the one-wayness of a public key cryptography. This broken if there is a quantum computers with more than 1,000 qubits. So private key, public key, small to capital, this way is done easily, but inverse is almost impossible, but it can be made possible with a quantum computer. So the inverse operation can be done with a quantum computer. Why? Because there is something called Shor algorithm, which was invented in the 1980s at MIT. And basically, uh, given the difficulty of Bitcoin, POW, I mean, not the difficulty, but given the fact that uh, the Bitcoin uses this cryptography, which happens to be vulnerable to Shor algorithm, right? Then the Bitcoin stored in a public key back in the early Satoshi Nakamoto days. All those payments will be vulnerable to be broken by quantum computers. Okay. So that's the thing that we have to prepare, okay, in order to prevent such events. Okay. So there is a elliptic curve cryptography. You can read about it. Nice examples I have given, right? So it is a one-way function again. Basically here, as you can see, K is a private key, small k, large K is a public key. You select a random integer K in a large number space, and then computing the public key is adding that integer G times, adding integer G times. So this K is a small k multiplied by G. G is an elliptic curve point, basically here. So the elliptic curve looks something like that. And there is a point, select as initial number, and then you add this k times, small k times, then you finally get a point somewhere in this elliptic curve. That is your k. But as the way this elliptic curve designed, it is very difficult to guess how many times G has been added to obtain capital K. So that is very difficult to track back. Okay, so it is very difficult to find K, small k. All right, so that's what cryptography. Here we have a sign algorithm. Then once you have that uh, one-way function designed, then all you can do is you need to sign the message. So here, sign message, basically a transaction. You put this as an input, then you get the signature. Okay, signature. Then you get the signature. Okay, then you can do sign your transaction, right? Use this algorithm that NIST published, right? And then others will verify, okay? Verify the sign, verify sign with the public key. Then this is going to be valid or invalid. That is the cryptographic function that NIST has published, so that people have been using it. So Satoshi Nakamoto utilized it for Bitcoin system. All right, and as this becomes vulnerable, so paying to the public key of Bitcoin, I mean public key, pay to, public key. This type of payment is known to be vulnerable when there is a quantum computer. So people are basically upgraded to pay to public key hash. It utilizes a hash function. Okay, and then basically people uses address. So from the public key, now they use a Bitcoin address. Okay? And basically it goes from the public key SHA-256, another hash function, and then base 58 check. So this one is used to prevent from human errors. And then that is what you have, address. Okay? So address looks something like this. Okay, you can read about it. All right, so that's the operation that we are talking about. And then you finally get the hash, the Bitcoin address. Basically, base 58 check is removing these numbers from the, ASCII key. Okay? All right, then you take a look at the actual Bitcoin belong to an address. You can search through the Bitcoin network. Basically, you get the output, something like that. Okay. All right, and there is a UTXO on standard transaction output, right? I think I have to do this later on, right? But you can read about it, UTXO, and then change, how change is made, and how to create a transaction, what the transaction look like, and how do you spend, and key difference to Ethereum, and locking script. Bitcoin is basically scripting language. Okay, it uses scripting language, and then uses this scripting language to create transaction, and then how to verify if this transaction is valid, how to check the signature. That's all there is to it. And then there is operation table, stack operations, and then numeric operations like plus, minus, multiply, division. Those things are defined. And then you use this script to check the validity of transaction. Okay. I will cover this later on. All right. But by the way, you can take a look at this note, and then lecture is pretty illustrative. I hope you can understand. Next time I will talk about this in class. Okay. All right. Wednesday there is no class, and then I will catch up with the class materials later on. All right. Wednesday there is no class. All right. Monday next week we will have a class. All right. I'll stop right here. See you Monday next week. Bye. Bye bye.